This is a kit for a gyroscope with LEDs on it that you can spin and it will light up. And I wanted this for something where maybe I could do things like detect when light is present or not. Even something as simple as if I have some sort of light detecting sensor and I were to spin a gyroscope with an LED on it, maybe I could detect when it stops spinning and use that to trigger another circuit. So I wanted to give this a try when I saw it on AliExpress. It uses two CR2032 batteries, not included, so I have a couple of those. It looks like the batteries are in series to give a 6-volt supply, and it's an NPN Transistor Astable Multivibrator, where we have two LEDs that will come on with the other two off. Then those two will go on, the first two will go off, and it will go back and forth. So whenever it's spinning, it'll do some sort of pattern. We'll have to see. So we have 1K series current limit resistors on the LEDs, and the timing that controls the flash rate back and forth is controlled by a 1 meg resistor and a 100 nano capacitor, controlling how long it takes each transistor to turn on and off. So when this is all finished, I'm going to put scope probes on a few areas here. So hopefully it's a straightforward kit to put together. The parts are through hole, so that's easy enough. I assume this to be the switch for the power. It seems to be some sort of a spring contact in there, and when you pick it up and start moving it, power comes on and turns on those LEDs. So here we have one terminal going to what looks like a springy mechanism, and then the other terminal has a blade contact here. So it looks like if this thing moves enough, it will hit against the other terminal, making contact. I assume they know what they're doing, and when this spins, it'll make better contact. It's always impossible to read the color codes on these blue background resistors. 1 meg and 1K. So, of course, I like to put the low-lying components on the board first, and that would be the resistors now. So these two 1 meg R3 and R4. R3 and 4 are the top and bottom resistors. And the silk screen shows 1K and 1 meg where they go anyway. So I'll just bend those out to hold it in place. And I'll use this mechanic 0.8 millimeter 6337. So it's not the thinnest stuff, so it's good for through hole. So I make contact with the component lead and the pad on the board simultaneously, and then make the connection and cut the leads. So I'll keep the leads because sometimes you need to make some sort of a wire connection on another project, and I use these all the time. Like if I wanted to short one terminal to another, I can just use this. And another use for these leads, if I bend them over so it's like a 2-pin short, if I put that in a breadboard on the same row, so the 2 pins are really in the same line, now I can clip a scope probe or just touch a multimeter there using this as a test point or a ground clip area or something. Now I'll just put the other 1K resistors in, just bending them by holding the resistor and bending those down roughly into shape, pushing it all the way flat, bend the leads to make sure it'll stay. Now the resistors are done. I'll put the capacitors next. There's only one value capacitor and there's only 2 of them on the board, so they just go in. Now I think I'll put the LEDs. Cathode goes to the resistor, so that would be this row of pins closest to the resistor being cathode, and cathode is the shortest lead. So I'll just put the cathode toward each resistor and trying to keep those flat, bending these leads. It's not as easy as a resistor, so I'm going to just tape these down to get started and do one terminal on each LED. So those all look aligned and flat to the board, so I'll do the other side. Transistors next. S9013 like it says on the schematic, and the silk screen shows where the flat face goes. Now there's really only that switch and the two battery holders and then the mechanical stuff, and they are showing what part of this switch has that terminal and the nearby spring. So this is the open contact part, which goes there. That should be right. Now I have to reflow this one terminal because this is slightly up in the air, and I'll push it down. Now it's flat to the board. Now for the battery terminals, I'm going to put some of this on this pad on each of these batteries, because when the battery goes into the holder, the negative terminal on the bottom has to make contact here, but if this is perfectly flat, that's going to have a hard time. Plus, building up a little hill will help battery retention possibly by putting this up against the battery holder. So I'm just trying to coat the surface, and that should be good enough. Now I'll put the battery holder down. They have a very small extra mark on one side, and the other side is all open. So I will assume that's where this tab goes, and that's the other side where the battery slides in. Which is good, because over here we do have clearance for the battery, but back here we'd be colliding with resistors. So I'll tape that down, and doing a test fit, that has room to go in and holds. I'll do the other one, and that should be it for the electrical stuff. And for the final mechanical assembly, I looked at the listing for this. It looks like this small piece just gets threaded all the way through, goes through the bottom. The longer one threads on from the top, and that's the surface that it spins on. So see what happens. There it goes, and it goes off camera over to the oscilloscope. So if I hold it slightly above the surface and start rotating and drop it, I think that might be the secret. So I'll turn off the light and see how the LEDs look. And now I can't see anything. I don't know if I'm in frame. Here goes. Ooh. And the camera can't really focus on that very well. And I think I need to zoom out. So now that we know it works, I'm going to get it hooked up and see what's actually happening with this Astable Multivibrator. Now it's starting to look like a project. I have 4 scope probes. I added test point wires basically across both terminals of both capacitors in the circuit. And because the power switch needs physical motion, I put this momentary switch. So the LEDs will come on when I push this. So I can trigger on the Astable circuit. These are 10K resistors I put in parallel across the 1 meg resistors. So we'll look at the schematic while looking at the scope, and I'll explain why I did that. So the 1 meg resistors are the ones in the center, going between the positive supply, which is around maybe 6.2 volts with fresh batteries, and down to charge capacitors, as well as directly control the base of transistors. So these waveforms are from when I put a 10K resistor in parallel with each 1 meg resistor to get these waveforms to look more idealized. I was having trouble originally with the 1 meg resistors on channels 1 and 4, the top and bottom. When the transistor is on and we're supposed to see this side of the capacitor held to ground, as we are seeing here with this low period, with 1 meg resistors, this ramping up wasn't happening when a transistor switches again. It was going to ground, but then it was immediately starting to charge again. And I think it's got something to do maybe with these 1 meg resistors and these relatively small 100 nano capacitors don't really give enough drive strength to hold this transistor on. So it momentarily turns on, but then this capacitor doesn't stay at ground, it starts charging. So we're going to look at how the astable circuit works. So to begin, I marked 4 test point areas. I'm calling them 1, 2, 3, and 4. So that's the left and right side of one capacitor, and then the left and right side of the other capacitor. So 1 through 4 corresponds to top to bottom traces 1, 2, 3, 4. So this was just turning on the power switch and letting the circuit run, and I just captured some of the behavior. So we know when this circuit powers up and stabilizes, what we're getting is 2 LEDs on with the other 2 off, and then it switches to the other LEDs on with the first 2 off. So it goes back and forth very fast. With these circuit values, so each side is out of phase, but each side is running at 75 Hertz. All of the anodes of the LEDs are connected straight to the positive supply. The cathodes, through the current limit resistors, momentarily get connected to ground to turn on the LEDs when the transistor on each side happens to be on. So if this transistor is on, we get 2 LEDs on. When this transistor is on, we get 2 LEDs on. So we can look at the scope traces to see how this alternates once it's powered up. So on the base of each transistor, we do have a pull-up resistor to the positive rail, and assuming everything is discharged, capacitors have no voltage across them, and everything is at 0 volts, when we power on, we have this resistor connecting to this transistor base, and this one connecting to this transistor base, and because no 2 components are going to have identical specs, even with the same values, from the same manufacturing batch, basically one transistor is going to come on before the other. So we just need to pick a starting point and make an assumption that one or the other transistor happens to be on once we power up, and then we can start analyzing. So the 2 middle traces are channel 2 and 3, and those represent the base of this transistor here and the base of that transistor there. So I'm going to move this display over, and I'll use this cursor to move along. So at this point in time, the 3rd test point, which is the base on the first transistor, is charging, so it's not on in a steady state. This transistor is off. Channel 2, which is connected to the base of the 2nd transistor, is constant at 800 millivolts based on the readouts on the scope right here. The maximum the base of the transistor ever gets is 800 millivolts. So at this point in time, this transistor is on, which means this side of this capacitor is connected to ground or slightly above ground. So that's the 4th scope trace, and that's right here. It's at ground as long as that transistor is on. So then we have channels 1 and 3 kind of charging up to some certain voltage. So channel 1's the collector here, channel 3 is the base of that transistor. So if we skip to the next state change here, moving this cursor over, the thing that causes all of this to shift into this new condition is when channel 3, the base of this transistor, has charged up to 800 millivolts and turns on this transistor. So leading up to that time, this is charging up because this capacitor, having that side connected to ground and the other side going toward positive supply, it's trying to charge this capacitor, but because it's directly on the base, we're going to have the base emitter diode junction here, not allowing this voltage to ever exceed, in this case, 800 millivolts, which is what it takes to turn on the transistor. And then we just get a constant diode drop of 800 millivolts above ground. So we were charging up right here. we got to 800 millivolts, we couldn't go any higher, so it stayed at 800. So now this transistor is turned on. That means the first channel should go to ground on that side of that capacitor. So here, the first channel drops to ground as long as that transistor is turned on. And at the same time that this side of the capacitor starts getting grounded, the other side of the capacitor on channel 2 used to be held at 0.8 volts because this transistor used to be on, but suddenly that drops to a negative voltage right here. So based on the scope readings, this goes from 0.8 volts suddenly to minus 3.6 volts. And that's what we're seeing right there. So that now turns off this transistor because it's no longer forward biased at 800 millivolts. It's minus 3.6. And the reason we get a negative voltage there, before this transistor turned on and brought this side of the capacitor to ground, just before then, this side of the capacitor on that first channel had charged up to 4.4 volts. So we had plus 4.4 and plus 0.8 volts. So we had 3.6 volts across the capacitor, this side being more positive. Then when we instantly brought this capacitor to ground, when the transistor came on, we still had 3.6 volts across the capacitor, and this side is more positive. So now with this suddenly being ground and this side being more negative, with respect to ground, this became negative 3.6 volts. And that's what we see here. There's ground. It dropped from positive 0.8 down to negative 3.6. So that negative voltage that ends up here is just because prior to that moment, the left side of the capacitor was more positive than the right side, and it was charged with 3.6 volts. So by forcing the left side to suddenly zero and still having a charge and still having the left side more positive, this had to become negative 3.6 with respect to what is now the 0 volt side. So now with the base of this transistor getting negative 3.6 volts, this transistor is off. So channel 4, that side of that capacitor, now starts going as positive as it can toward the positive rail. It ramps up, and the left side of this capacitor, since it's turning on this transistor right now, that's fixed at 800 millivolts. The collector's being brought to ground, and after the instantaneous minus 3.6 volts, with this side of the capacitor connected to ground, and this being below 800 millivolts, the capacitor now can start charging toward the positive rail again. So channel 2, we see it charging. But again, when it tries to go higher than 800 millivolts, it gets stuck at 800 because of the base emitter diode junction again, holding this fixed at a max 800 millivolts. So if we move the cursor along to the end of that process, so right now the thing that's occurring of interest is channel 2 is charging up from that negative 3.6 volts, and when it gets high enough to turn on this transistor, that'll be the next state change. So this is going to try and charge through this side of the capacitor being connected to ground, and here we have a path with the resistor up toward positive rail. It's charging up from the negative 3.6, but once it gets to 800 millivolts again, it can't go any higher because we have the voltage base emitter diode junction holding this at a max of 800 millivolts. So with the voltage here rising enough to turn this transistor on, we're in this portion of the whole process. Channel 2, the transistor comes on with 800 millivolts. That again connects channel 4, that side of the capacitor, to ground. So that's right here. Soon as the base could turn on the transistor, channel 4 goes to ground. But just before this side of the capacitor went to ground, it was charged up around 4.4 volts, the highest it could get toward the VCC rail. And this transistor was on, so we had 800 millivolts on the other side of the capacitor. So the right side was positive 4.4, the left side was positive 0.8, so we had 3.6 across the capacitor, the right side being more positive. So when we bring this side of the capacitor to ground, we still had a charge of 3.6 volts across it, with the right side being more positive. But now that we've forced the right side to 0, the left side is 3.6 volts below ground because it's the more negative side of the capacitor. So that's what we see right here. Channel 3, we were at 800 millivolts. As soon as we put the other side to 0 volts, the left side dropped from 800 millivolts down to minus 3.6 volts. So that turns off the first transistor, and now this node again can start charging because we have ground on one side and now we are connecting to the positive rail. And because we're not forward biased, we're not stuck at 800 millivolts here, so we're at minus 3.6. We're free to start charging until we get to 800 millivolts again later, which will happen over here. And while this transistor has switched off, channel 1, which used to be connected to ground, is now not connected here. So it starts climbing toward, and the camera shut off because the memory card was full. I think I was saying something about a capacitor. This first transistor, when it was on, back in this point in time, this side of this capacitor used to be at ground, but now with this transistor off, and so this is disconnected from ground, this side of the capacitor is free to move toward the positive rail, which is what it starts doing here when the base of that transistor went to negative 3.6, turning off the transistor, and then it's on its way to charging back up toward 800 millivolts so that this can turn on again. So the cycle then repeats, and we get one bank of 2 LEDs on or the other bank, and the speed of that alternating flashing is controlled by the time constant of the resistor capacitor networks here, controlling when each transistor comes on. And that's how the Astable Multivibrator works.